Okay, everyone. Good morning. Today we're gonna cover this. Sorry, finish the slides from yesterday. So you already have them. So come on, get them out. So I think we finished 4 pages yesterday. Today we're gonna finish the last 4 pages. Okay. No, no. I gave you the whole package yesterday. So we finished the first half. Now today we finished the second half. Yep. Oh yes. There we go. Does anyone not have the package from yesterday? Good. Yes. Thank you. Here. We're good. Everyone has it. Sounds good. So before we start, I just want to say I'm sorry about I guess maybe some of you were expecting the quiz yesterday. Just long day of just marking and doing other stuff as well. So yeah, so I knew that when I pushed it, people would like that. That's absolutely fine. So you're right. There you go. So hopefully I'm gonna get it posted today. Posted today at like 5, and the marks still working on them. Hopefully they will be finished by tonight as well. Okay. Um, so if we post the quiz today, I guess today is Wednesday. So Wednesday, Tuesday, Thursday, maybe it's Wednesday, Thursday, Wednesday. I'm counting backwards. Wednesday, Thursday, Friday, and if we need to push it to Saturday, I'm absolutely okay with that. Okay. All right. No problem. Okay. So let's recap. What did we cover yesterday? Kinematic graphs. Okay. So in a nutshell, we said there are how many types or kinds of kinematic graphs? 3. The first one, the major one, is what is position versus time, and then the one after is velocity over time or with time, and then the last one is which one of those 3 are we not going to bother doing? Acceleration versus time. It's still kind of like the same message. If you know how to do the first 2, you know how to do that one, but we're just going to skip it. Okay. And we acted out a position time graph. Okay, I acted it out in complete detail, this one. And we concluded one important thing. A flat line, a flat level horizontal line on a position time graph, what does it mean? You kept the same position, which means in physical terms, you held your position. Exactly. You stopped moving. You're not moving. Okay. What does an increasing line mean? You're getting further and further from the what? From the origin in the what? In the whatever direction the thing tells you. And then if it's decreasing, you're getting what? Exactly. Kind of like closer back to the origin, and maybe you overshoot it. When do you only overshoot? If it goes what? If it goes below. If it goes into the negative west, which means positive east. Good. And we said that definitely whenever you have a bunch of straight lines, what can you always calculate with them? Slopes. Yes. And the slope idea is the exact same thing from grade 9 and 10. You just do the rise over run. Okay. And what did we conclude from these red boxes? Is that velocity is obtained by finding the what? Of which graph? Of the position versus time graph. Okay. Then we went to what? Velocity time. And we almost started the same way. And we acted out a velocity time profile. But now, what does a flat line mean when it comes to VT? You are holding your speed, which means that means what? Standing, or you're what? Exactly. You are cruising at whatever speed you just got to. What does an increasing line mean? You're actually what? You're accelerating or speeding up. What does a decreasing line mean? You are slowing down or decelerating, which means are you reversing? But are you kind of like being pulled backward? Yes, something is what is kind of like pulling on you, not with your motion, but against your motion. Good. And we explained, or sorry, described the entire motion. All right. So everyone, go ahead. Let's calculate the what? The slope of these 5. So identical to the exact same idea. But now instead of D, I have what here? I have V's with an arrow. So go ahead, put an arrow on top. How many line segments do I have? How many line segments? 5. 1, 2, 3, 4, 5. Again, two of them must have positive slope, 2, the first one and the third one. Two of them must have zero slope, the second and the fourth. And the very last one decelerates, which means, as far as velocity is concerned, it has a negative slope. Okay? So I guess I'll just show you a bunch, and then you can just do the rest on your own. Yes. Oh, really? Oh, right here, right here. It was one whole package together. Yeah. We are doing. This is yes. Yeah. So we're here. Actually, we are this way. Ah, all right. So let's go to the first one. Can someone tell me for the first segment what was the initial time for the first segment? 0. What was the final time for the same first segment? Uh, final time for the first line. 6. 6. So Ti is 0, Tf is 6. How about the y-axis? What was the initial velocity? Initial velocity of that segment? 0. It started from a height of 0, and it got all the way up by the end of the 6 minutes to what? To 8 meters per minute in the south direction. So there we go. So slope number 1, literally the same amount of work. However, do these two cancel out? No, they don't. They look like it, but they don't. And what's the proof again that they don't cancel out? If they cancel out, what's the only one that survives? Meters. You cannot what? You cannot measure acceleration using what? Just meters. You need what? Meters per minute squared. So ladies and gentlemen, we just discovered that if you do the slope, of a velocity time graph, what do you obtain? You obtain something with a squared minute or squared time, which means what? This is what acceleration is. Exactly. So go ahead. There we go. There we go. Okay. I want to print something for you, so I'm just going to freeze the screen because I actually need to use the USB. Okay. What's the slope for the first segment? Positive or negative? Is that expected? Yes, because the line was on the what? On the drop or on the rise? It was rising. Things were values were increasing, which means that's positive. And then what happened to my speed? It what? It cruised, so that means it was kept the same or it did not change. In calculus terms, that means the rate of change was 0. Literally, that's exactly what that means as well. And again, what? I sped up even more. That's why this number is what compared to this number? Come on, this number is what compared to that number? Oh yeah, higher, like almost 4 times higher. Why? Look what happened here. Here you had how much time? 6 minutes. And how much of a gain did you get? Or did you? Okay, here you only have what? And how much of a gain did you do? Wow! Imagine half the time, and you went through what double the gain. So that makes sense that the slope is really steep. Okay, and then you cruised or leveled off. What happened here in the fifth segment? From 15 minutes all the way to 24 minutes. What happened to my velocity? I slowed down to a what? To a 0, to a complete dead stop. Okay, so obviously since things start what decreasing, what kind of a slope am I expecting? Negative 2.76. Yeah, that makes sense. I have lost 20. I have lost. This is what lost means. I have lost 24 meters per minute of speed or velocity over 9 minutes. That means my rate of loss was 2.67 meters per minute every single minute. Okay, which one of those are we going to flip? Which one did we flip in the slopes for the position time? Which one do you always flip? Which kind of vector do you always flip? A one with a what? With a negative magnitude or a negative sign before the magnitude. So which one of those are we going to flip? The last one. Actually, I won't. Ladies and gentlemen, the only thing you do not need to flip is what? Is which vector? acceleration. Why is that? Because think of it. What does exactly positive acceleration means? What? You're what? You're speeding up something, you were moving forward, and then something also what pushed you forward. What does negative acceleration mean? You're still moving forward, but something is what? So the only one that you never need to flip is the what? Is acceleration, because actually the negative sign is the most important part of the story. So never flip acceleration. Keep it negative because that tells you exactly what that tells. Okay, let me ask you a question here. Everyone, pencils down, eyes on me. Okay, what was I doing? I speed up. So I was moving forward, and my acceleration was also what? No, my acceleration was also which way? Forward. My acceleration, what? My push. Whoever was pushing with the motion. How about now? I slowed down. So I was what? Decelerating. When you decelerate forward, that means you're accelerating what? You see? But you see how confusing that might lead you to think? That's why I don't want you to flip this. Because if you flip this one, what would this one become? And this becomes what? So then you're gonna be like, I am accelerating at 2.67 north. Why did you just saying I'm just what? Decelerating, which means what? I'm losing speed. Do you see what I mean? Never flip acceleration. If you have a minus with acceleration, keep it. What if you have a minus with velocity or displacement? That what you do. That you flip because that literally tells you what where you need to move, not how you're moving. This is how you're moving. The other ones were where you're moving. So that's why the other ones needed to be positive. Okay. So what did we conclude here? What unit do you measure? Sorry, what unit does meters? My bad. What do you measure using meters per minute squared? Acceleration. So now we have another what? Another pearl of wisdom. Acceleration is the velocity. Sorry, acceleration is the slope of which graph? Yeah, the velocity was the slope of position time. Acceleration is the slope of velocity time. You see, each one generates something as a sequence. Okay, does anyone know who that is? That would tell me how well. I know how young you are already, but does anyone know who what character this is? Sorry, what? Nope. Gentlemen, who knows Mortal Kombat? Mortal Kombat. That's Lord Raiden. Lord Raiden, the Lord of Lightning and Thunder. Okay, from the Sega game, he wears the hat, but in the movie, he did not wear the hat once. This was the original Mortal Kombat movie that was made in 1996. You were not even an idea then, not just born. Probably your mom didn't even meet your dad by then. Okay, that's Lord Raiden, Lord of God of Lightning and Thunder. That was my childhood right there. Okay, all right. Yeah, actually, it's amazing. This is the first class ever where no one knows him. I guess the more I teach, the younger the kids will get, and then they will from the Sega game. Yes. Who even plays Sega anymore? Weird, man. Sega was the thing in the 90s. Everything was Sonic, Sonic, Sonic. Well, Sonic is the best. It's the flagship for the whole franchise. Sonic, and they were almost the first ones to come up with a soccer game, and then Nintendo just beat the crap out of them. Mario, yes, and King Kong, and so on. Yeah. Oh, sorry, Donkey Kong. Okay. All right. Okay. Let's do a practice worksheet, everyone. So consider the following velocity time graph, or I'm already telling you, it's a what kind of graph? By the way, if I just gave you this and I gave you time, but I didn't tell you what this one is, can you even proceed with analyzing the graph? No, exactly, because if you think of it as position time, it could lead to a different interpretation than what? Than a what? Acceleration time. You need to know what this means, otherwise you cannot even interpret what this describes. Okay, so so it's heading west along a what? Along a along a straight road, which means what? What doesn't change? Direction. Thank you. Also, consider all numbers to what? Yeah, so I know that 30, by the way, you're going to find out that many scientists and mathematicians, by the way, how many digits show here? Two. Actually, there is one of the rules in sig figs, which I am hoping to cover on Friday. I need to get done with the sig fig for once and for all. They actually say that whenever there are a bunch of zeros at the end of an integer, they do not count as what sig fig. So what really counts is just the what? The one. So here's one sig fig, one sig fig, one sig fig. Again, I'll explain the rules. But let's say assume everything is to what? So as if it was 60.0, 50.0, 40.0, and so on. Okay. Uh, Baha, what's the first question? What's part A of the question? Huh. Is the overall motion from beginning to end a uniform motion? How many people say no? Okay, you have to give me a reason. Hannah, go ahead. Give me a reason why this in no way represents uniform motion. By the way, easy way to think about it, think of the two conditions that have to be met. Again, Hannah, have to be met for uniform motion to exist. Going up. I need more detail. Because remember, going up is a very vague statement. What is not consistent? So, okay, everyone, what did we say? Okay, remember worksheet number 3, the accelerating car? Why did we say it was not representing uniform motion? Baha? How did we say it exactly? What was changing? The speed. Do you see what I mean? Remember, uniform motion means what? What do you keep the same? Exactly. The vector direction and the vector magnitude have to stay the what? Is the vector direction staying the same the whole time? No, here. Yes. Is it the same value all the time? Not from start to finish. So that means what? No. So we're going to say no. Thank you. Because actually, you can literally say the same thing we said in worksheet 3. Because the speed is not constant or fixed. Because speed, you can say speed or velocity. I really don't care. Speed is not constant slash fixed. Okay. All right. We agree with that. However, is it uniform motion sometimes? Is it cruise controlling sometimes? Where? What intervals or regions of time is it? Omar, give me one. You have to give me from beginning to end. Because remember, you can't just say in 10 minutes. You have to tell me from when to when. Yes. So in the interval of 10 minutes to 20 minutes, and also what? 25 to 40. Great. That's it. Only 2 times it keeps the same cruising speed. So go ahead. Yes. It cruises. Cruises. UI. Cruises during. Okay. Two. So during the first one, we can say 10 minutes. Oh, is it? My bad. It is hours. Sorry. 10 hours to 20 hours, and then the train. Uh-huh. What was the other one? It's a train car. What? It's a driverless car. It's one of those Google cars. There you go. Yeah. Okay. How about the regions, the other regions in general? Okay. So part C says what? Determine the average acceleration in in what? Miles. My bad. Miles per hour squared of the car during the following intervals. Okay. And there's a reason I'm picking these intervals. So the first interval is what? 0 to what? 0 to 10. Okay, everyone, let's zoom in on the graph and see. Okay, 0 to 10. So what was the initial velocity at 0? Apparently 0. So by the way, everyone, we can do 0 here and 0 here. What was the final velocity at 10 hours of motion? What do you think that is? Yeah, it again, by the way, unless you have a perfect grid to look, we're okay estimating. I'm always gonna give you a perfect grid. But here, yeah, I meant it to be perfectly in the middle between 50 and 60, which is 55. So go ahead. we're going to do the equation as we did before. I'm going to do AV equals 55. 55? Yes. And let's, by the way, since we need them to be 3 sig figs, let's put a 0 at the end. 0 miles per hour. In which direction? West, minus 0 miles per hour, also west. All dividing 10 hours minus 0 hours. Okay? So what's the answer? 55 minus 0 is 55 miles per hour over 10 hours in the west direction. What's 55 divided by 10? Any number divided by a power of 10. You just play with the decimal. So 5.5. Remember, it needs to be exactly 5.5 is 2 digits. We need 3, so 5.50 miles per hour squared. Technically, still in the west direction. Yes, Sally. Yeah, remember? I kind of did that sometimes. Today I just chose to put them back in. 100%. Intermediate step are completely your own choice. Just remember to put everything back as a final answer. Okay. How about 15 hours to 30 hours? 15 hours to 30 hours. So from here to here. Okay, everyone, I have a question for you. Listen up. Acceleration. Is it a vector or scalar? By definition. Acceleration. By definition. Acceleration depends on velocity change, which means it makes it a vector. Okay. The reason I asked you for from 15 to 30 is how many line segments are contained in between 15 and 30? Technically 3. You've got a cruising part, you've got a decelerating part, and you've got another what? Another cruising part. What do you say to someone who says, "Oh, okay, I have 3 things, and I'm calculating the." This is where people get confused. What do you usually do? Okay, everyone, how many people here are taking 4 courses this term? 4 courses this term, mostly everyone. How do you calculate your average at the end of each term? How do you calculate your average in 4 courses, or 10 courses, or 2 courses? You add them up. You add everything up, and then you divide by what? 4 or 5 or whatever number of players are going into the mix. How many different regions or segments do I have here? So someone says, okay, I will get the average acceleration over what? Over this, and get myself a number. Then I'm gonna get my acceleration over this, get myself a number. Get my acceleration over this, get myself a number, and then do what with the 3 numbers? Add them up and then divide by 3, because I'm trying to calculate the what? The average. You see where the word average could really destroy how you think about average in statistics is different than average in what? In physics. Because average in statistics just means what? I've got a class of students. I'm going to collect all your marks, add them up, and then divide by the what? By the number of students. That's how markable gets you what? The class average. That's a no-brainer. That's ABC of statistics, right? We all know this. When you do average, when it comes to physics, you do average with respect to what? With respect to time. What does that mean? Do you actually do it the statistics way, or do you just do final minus initial? Do you see why I asked you, is acceleration a vector or a scalar? When you average a bunch of scalars, what do you actually do? Do you do it the physics way or the statistics way? A bunch of scalars. How about when you average a vector over time? What do you do? Tell me something about displacement. Is displacement a vector or a scalar? A vector. Did displacement care about intermediate steps? There you go. Displacement was which kind of observer? Active or passive displacement? Displacement was passive, which means what? You didn't care about what happened in the middle. You only cared about what? The beginning and the end. Do you see what I mean here? That's why, and again, I would have never said that had it not been for a student I had 12 years ago, where I asked them to calculate the average in this graph, and they did what? They did this one, They did this one. They did this one. Obviously, I didn't understand why they did. So I asked, why did you do it that way? They're like, because that's how you do average. And you know what? Were they wrong thinking that? No, they've never thought of average in a different way than the statistical average of a bunch of scalar numbers, not a bunch of vectors. By the way, question for you. How would you have done it if you did the scalar way? What's the slope over here? There is no change. So what's the slope of a flat line? 0. What's the slope here? Yet another 0. What's the slope here? Positive or negative? Negative, because you're going what? You're losing value. You're losing velocity. You're going from what? 55 down to just what? Just 40. So that's what they did. They added 0 plus whatever negative over those, and they did. Completely wrong. What do we just do? We do final minus. It's as if there's a line directly connecting what? Right? Vectors always connect initial to what? Vectors never care about what? Intermediate step. Thank you. So let's do this. I just wanted to make sure that we understand that. So a scalar average is not the same as a vector average. All right, let's do this. So AV equals, what was the velocity at 30 hours? 30 hours. It was 40. And to Sally's point, I'm going to skip what? Both the direction and the what? And the unit. Skip them. So 40 minus what? Oh, okay. Good question. Thank you. If all the units, sorry, yes, if all the units are the same or consistent across the entire problem, leave them. Just remember to put the proper ones at the end. As far as directions are concerned, you only skip them if they are what? All pointing in the what? In the same direction. Okay? So obviously, because everything technically is given to west, we're just gonna skip it. So 40 minus 55, all dividing whatever that is, 30 minus 15. All right. What is 40 minus 55? 40 minus 55. 15 with a negative, so negative 15 over 15. Technically 15.0 and 15.0. What's negative 15 divided by 15? A solid what? A solid negative 1. So it's a negative 1. Now what do I put back? Come on. I put back both the direction and the unit. So it's negative 1. Actually, I have more space here. Negative 1.00. What's the unit now? I mean, you don't even have to guess. I'm telling you. What? Miles per hour. I'm always going to remind you what unit to use. So miles per hour squared. In which direction? Do we need to flip it? I mean, if you can, but do you need to? No, because this is what vector? Is it displacement, velocity, or acceleration? Is it good to have a minus? Because it tells you, are you speeding up or slowing down? You do, because overall, did your curve go up? Sorry, did your velocity graph go up between those 2 points or go down? You lost an average of what? 15 miles per hour over 15 hours. Perfect. So you're losing 1 mile per hour for every single hour of decelerating. Make sense? That's it. All right. Who can do this in one shot? Why? How many people say this is 0 without doing any math? But why? Exactly. I'm going from what? 0 to, again, it's an average. But do I care about what happened in the middle? That would be that would be the average over segment 1, segment 2, segment 3, segment 4, segment 5. But are we averaging a scalar or a vector? We're averaging a vector over time. You do not care about the intermediates. You just go from beginning to end. What was the velocity at the beginning? What was the velocity at the very end? As far as you're concerned, you did not see a velocity change. Done. That's it. So we can just say what? Since no v change over this period, that implies average acceleration only over all that is what? Well, technically we have to write it correctly. 0, yes, 0 miles per hour squared in the technically west direction. Nice. I'm a big fan of shortcuts. Use them once you know why they work. Graphical representation of motion. Okay, let's do the first one. Everyone, come on. No motion. Tell me if I'm not moving. Everyone, if I'm not moving, am I changing my position or keeping it? Okay, so that means how should my position time graph look like for an object like me? Flat line. Does it have to be at the 0 level? It could be above or it depends. Am I west of the origin or east of the, like, am I on the positive side of the number line or the what? Negative side, okay? So we agree for a fact that, by the way, you have the, okay, so go ahead. What does no motion mean? Come on, write the what, the features. No motion means what? Same position all the time. What does that also mean about velocity? If you're keeping the same, if you're stopping at the same position all the time, what's your velocity all the time? I'm not moving. Exactly. Thank you. I'm zero. Speed and velocity. How about my acceleration? Come on. You're keeping it at 0, which means there is no change in velocity, which means you're not accelerating or decelerating. Nice. Okay. By the way, do you see how if everyone builds into something else? By the way, this is always the sequence. Position builds into what? Velocity builds into? Good. Okay. Let's compare this to what? To the graphs. What does same position mean? This way, or level line? Yeah, because your position has to stay the same as what? As time goes by. Thank you. All right. Okay. Fixed position. Go ahead. Come on, come on. Fixed position. By the way, a lot of the graphs are almost done for you. What you needed to write most is the what? Is the features on top. Okay. Question. What is simpler than that line? By the way, is that a slanted or a level line? What is 1 degree simpler or less complex than a level line? A level line where? On the 0 axis. Hey, what does that represent? What's my velocity? Yes. Yep. Okay. I am relating the feature to the graph. 0 velocity means your thick line has to be right there at the what? At the bottom, keeping 0 at all times. Okay. All right. How about my acceleration? You got it. Come on, come on, come on, come on, come on. There's a bit of copying for the next 5 or 10 minutes, but that's it. Oh, whatever is not on your slide. So you have to copy these 3 statements, and then whatever features on the graph, if there are any. Oh, they're okay. They're done for you. Good. Okay. So our first kind of motion was what? No motion. What's your next one? Okay. This is the what? The progression of calculus. Flat line leads to a 0 line, and a 0 line leads to what? A 0 line. Can you get simpler than a 0 line? So a 0 line keeps what? Generating itself. All right. Uniform motion. Everyone, am I uniform motion? Yeah. Is my position changing? Of course. If the origin was there, I am getting what? Closer or further? I was getting further and further. But I was getting further at what kind of pace? Thank you. Fixed constant pace. Which means? Of course. Okay. What can you say about my acceleration? No. You can do better. What's my acceleration? At what value? There you go. I am not accelerating or decelerating, which means my accelerating is not just the same. It's what value all the time? There you go. No acceleration at all, which means 0 acceleration. Okay, let's look at the what? Let's look at the graphs. Interesting. What did I start with now? I'm not starting from here. I'm starting from what? and I'm building backward. Okay, what does no acceleration mean? Where should my line be? On the 0 line. Okay, I am not going to go down in complexity. I'm going to go up. What is more complex than this guy? So a level line, same level or above? You got it. Which means what? Thank you. What do you call that? Starts with C. Cruising. Thank you. That's what cruising means. You're keeping the same speed. What's more complex than a level line above the axis? A slanted line going up. Go ahead. Everyone, shh, everyone, eyes on me. Uh, everyone, are you seeing how each one, come on, are you seeing how each one relates to one? By the way, if you're taking first year physics, so first year in university, a big part of the first midterm test, especially with multiple choice questions, are these things, which is sad because that means what? You don't get to show your work. You either get it right or get a 0. Okay, let's keep going. What's Baha? What's my next motion after uniform motion? I could have accelerating or. So let's do the accelerating one. When you accelerate, is your position changing from the origin? Oh, yes. At a much faster what? Rate or pace. Thank you. Rate or pace. They mean the same thing. What's happening to your speed when you accelerate? It goes up. However, we are talking about what kind of acceleration? Yeah, uniform acceleration. It's not like you're just going like this. You're holding the press on the gas and you're keeping the same hold. You're not going. No, you are accelerating the same amount every time. Okay. Can someone tell me how this one's gonna look like here? What does fixed acceleration mean? It's gotta be a level line, but is it gonna be at the 0 or above? It's not. It's level, but it's not 0. What does 0 acceleration mean? Or thank you. Or uniform motion. We already covered that. Good. So I'm gonna start from backwards. What is more complex than this guy? 1 degree more complex. Only 1 degree more complex. No. Remember, level, slanted. What is 1 degree more complex than a straight line? Sorry, not just any curve. Think function. What is more complex than lines? Thank you. A parabola, a quadratic. Think about it. By the way, can someone tell me what's the equation of a straight line? Y equals mx plus b. What's the power or the exponent on top of the x? 1. So what's the next power? 2. That makes it a quadratic. Okay, by the way, y equals mx plus b is what we call a linear function because it has a degree of what? What's next? Degree 2. That's what quadratics and parabolas are. So I have to what? I have to, technically you have to sketch a perfect parabolic shape. By the way, everyone, does it matter where you start this line? Do you have enough information to say where it starts? You don't. You just know it's going up because you're accelerating. You're above the 0. Same thing. Do you know where you start this curve? No, you don't know where your position started. You just know you're getting further from the origin, like higher, higher, higher as time goes by. What's my last one? Come on. Decelerating. So if you're decelerating, do you have a positive acceleration or a negative one? This time I'm going to take this line and bring it below. Okay? You see how this one looks different? Why did I Why did I do it this way? Because where do I need to put my accelerating level line now? Negative level. What does that mean? Are you gaining velocity or losing? So should that be a slanted line up or a slanted line down? You are losing height. Yes. Do you still have to do a parabola? Yes, you still have to do a parabola because what is more complex than a slanted line? A parabola. However, now you have to be what? Now you have to be careful. Your parabola cannot be what? Increasing. You are getting further. Everyone, look, everyone, question for you. Pencils down. This board is my origin. This board is my origin. What am I doing? I'm speeding up, which means was I getting further from the origin? And was my pace even getting bigger? So that means what? It was a parabola going up. Now, everyone, my origin again. Was I still getting further from the origin? But what was happening to my speed? Was it increasing or plateauing? There you go. How many people have heard of the word plateau before? When you work out, after a while, what happens to the muscle response? Exactly. It gets used to it. So that's what they call a what? A plateau. A plateau means what? You're still gaining muscle mass, but it's getting what? A smaller gain. Like let's say, for example, the muscle was increasing at like 1 inch, for example, per week. Now it's what? 0.5 inch per, but it's still growing, but what? At a what? At the same rate or lower rate? You got it. Yes. So that means, and when you plateau, we also what? Shock the system again. Change your workout cycle. All of that stuff. Trick the system. You see how it plateaus? By the way, is this still an increasing curve? But what's happening to the slope? You got it. What was happening to the other slope? That's an increasing slope. That's a what? That's a decreasing slope. By the way, all this will be calculus. Yes, go ahead. Yes, exactly. Concave up, concave down. You're going to get used to these words. Nice. By the way, how many people can see the red lines here? What do these red lines mean? Slope segment. What's happening to the slope? It's getting more what? It's getting more level. Exact. It's always straight. It's plateauing. You got it. Nice. All right. Okay. Do you see the progress now? Do you see the basically the evolution? Flat line goes down to what? Goes down to what? So slanted line goes down to what? Flat line goes to what? Curve always goes to what? But it could be what? No, it could be up or if a curve is if the slanted line is increasing, the flat line is what? Above or below the zero? Above. If the slanted line is decreasing, the flat line is what? Below. I just taught you calculus. I legit just taught you calculus. You will remember what I said when you do the exact same thing with Mr. Shepard, because he will actually be what? By the way, the only way to teach calculus is to do it through an example, and the only example they can teach calculus with is kinematics. There you go. Okay? All right. Starting from a kinematic graph, then the process of taking the slope produces a graph that is what? That is what? Less complex. Less curved, if you say. Okay? All right. Don't worry, don't worry. Well, I want to make sure that I finish this. What if you want to go backwards? Everyone? What if you need to go, of course, and we did it a couple of times, right? We started the acceleration and we pulled what? We pulled backward and we increased the complexity, okay? So what if we want to go backwards? Basically, let me just read it with you. Oh, my bad. Basically, what is the reverse of taking the what? Ladies and gentlemen, who are these two gentlemen? Sir Isaac Newton on the left side, England. Sadly, the gentleman on the right is less known, but he should be as known. Gottfried Leibniz. Leibniz or Leibniz. L-I-E-B. Yeah, he's German. Leibniz. Those two invented calculus. Everyone, listen up. Just a bit, listen up. Just a bit of a historical introduction. They invented it at the same time. However, Newton, what's Newton famous for? Which we're going to cover a lot in Unit 2. Not just physics, in forces, gravity, but also what Newton's laws of motion. Newton's first law, second law, and so he was a physicist. He invented calculus just to solve what? Physics problem. To solve what? To solve basically, if I drop this in vacuum, they could not analyze drag forces in air. If I drop it, how much acceleration does it build up to? Like, what's the function that tells me how much speed does it get after 1 second, 2 seconds, 3 seconds, and so on? So actually, that's okay. It depends on the weight only if there's air drag. That was, by the way, does anyone remember Galileo's experiment? He dropped what from the Tower of Pisa? A feather and a bowling ball, or a ball. He said they should reach the ground at the what? They didn't. You know why? Because of air drag. I'll show you a beautiful video. Some of you might have seen it before. NASA eliminated what? Air drag in a vacuum chamber. They proved Galileo right. He just couldn't back then because he could not eliminate what? Air drag. Okay, it has to be there. So, what's the deal with Leibniz? He was a mathematician. He invented calculus from the what? From the mathematical perspective. I studied physics. I studied calculus with more what? With more physics application. I'm an applied mathematician. Mr. Shivers is a what? Pure mathematician. He studied the what? The mathematical foundation of calculus. By the way, both are important. He advanced it using physics. He made sure that everything is 100% correct theorem-wise for computers to work right and not have a glitch even one. Okay? So, what's the opposite, basically, of what's the opposite of finding the slope? Ladies and gentlemen, taking the area or finding the area. How many people know people who already are in first year engineering class? Ask them, not now, wait until December. Ask them, what are they covering in math? In first year math, in first term math. They will tell you, oh, we were done with what? Everyone, they'll tell you, we are done with what? How many people have heard the word differentiation? If you ever heard it. Differentiation is the calculus way of what? Finding the slope. They always do that from now until mid-November. And then everything until the end of the course is what? That's the word integration. If you ever heard differentiation and integration, they are what? Opposite, not just two what? Opposite processes. Girls and gentlemen, I'm going to teach them to you using what? Physics and kinematics. Okay? So, when they integrate in first year calculus, they are finding the what? When they differentiate, they are finding the what? Both Leibniz and Newton invented it to be like that. Okay? Oh, this is what it actually is based on. Yes, it's an equation that tells you the slope of a curve. Yes, that's my degree. My degree is in physics, all of that. Okay. Are reverses of each other. Go ahead. You still have to copy that? Or? Nope. All right. So, I just taught you calculus. Legit, I just taught you calculus. Okay. Now you actually understand the point of calculus more than taking a calculus course, just doing the math, because you know why we do it. Okay? All right. Everyone, let's find some areas. Hey, let's use the exact same example we used before. Do we have curves here or lines? Okay. Can you split this into a bunch of easy shapes? That's the beauty of what? Of lines. All the shapes are what? Could be what? What shapes have, everyone, what shapes have sharp edge geometry? Squares, rectangles, triangles, maybe trapezoids, right? Parallelogram, and so on. No curves whatsoever. Okay. By the way, is this the only way to split this up? No. How could you have split it? Could you have split, for example, maybe up to here, and then maybe this is as a trapezoid, right? By the way, I never use trapezoid. I try my best to only use what? Rectangles or squares or what? Triangles. Trapezoid, by the way, one reason for trapezoid. Not many people, for some reason, remember the area of a trapezoid. But everyone remembers the area of a what? Of a square, rectangle, and a what? A triangle. So you know what? Now, what shape is this? How about this one? How about this one? How about this one? How about this one? Exactly. That's technically a trapezoid now, right? It's what's a trapezoid, by the way? Two parallel bases, right? And two sides that are not the same. How can I cut this to make my life easier? Yep, cut it right here. So that's what we're gonna do right now. So go ahead. Okay, so we're gonna cut it into a bunch of areas and then do what with all the areas? Thank you. Get the combined total for all of them. All right. So where are we here? Okay. So okay. So go ahead, write this down, like some words. Well, only way we can find the total area is if we break it down. You just have to say break it down into areas we know. There are only two choices: triangles and rectangles. Obviously, do we have to say rectangles and squares? No, because every square is technically a what? No, but not every rectangle is a what? Exactly. The perfect rectangle is a square. Yes, a perfect rectangle is a square. No, no, I'm just telling you. Every square is a what? Is a rectangle. It's just a perfect rectangle of four identical sides. That's what I mean. No, that rectangle means what? Two opposite identical and two opposite, but two are shorter, two are long. That's what a rectangle is. A square is if all of them are the same. Okay, so let's look at this one now. Okay, this is area 1. This is area 2. This is area 3. This is area 4, 5, and 6. By the way, a question on your first unit test, which is not coming up until like 2 weeks or maybe even slightly longer, is I'm gonna give you bulk, a bulk profile. I'm gonna leave it completely up to you to what? To break it up and to what? And to add the whole thing up. Okay. Okay. Now what do we have here? So we show them now. Can someone tell me now? What's the by the way, what's the area of any rectangle? Rectangle. You can say length times width, like length times width, or base times. I like length times width. How about any triangle? Base times height divided by. And what's the good news about right triangles? You can tell what the base is, and you can tell what the height is. Like you don't have to go from the top point to the middle of the base. No, it's straight up. What's the base of the first triangle? How wide is it? No, no, the full right triangle, the full triangle first. How wide is it? Just how wide? 6. How high? Great. 6 and 8. How about the green rectangle? How wide? Yeah, not 6, not 9, in between. 3. How high? 8 it is. How wide is triangle number 3? I'm sorry, second. Which one? 2 or can 2 and 4 be a square? Actually, it can't. Think about it. This is 6 and this is 8. Right? By the way, is it bad to get a rectangle? The same amount of work you do for a rectangle area is the same amount of work you do for a square. You're still gonna multiply what? Length times height. It just happens to be what for a square? The same number squared. That's all. How wide is this distance? Yeah, it's not 9, it's 3. How high is it? Why is it not 24? Exactly. You're not what? And the most common mistake for people when they do what the area of triangle number 3 is that they say, oh, it's 24. Is it? No, it's only this much, which is what, Ali? How about this one? By the way, are those two identical? They are. 3 base, 8 height. You can want to take one double by 2. How about this one? How wide? How high? Fully. 24. How about this one? How wide? 9. How high? Fully. Perfect. All right. So now we can do what? We can actually do each one by itself. Okay. Let's put some numbers here. What was this one? What was the base and the height? Base and height. 6. Please put units. Not always. Just today. I'll tell you why. Put units. No. Hold on. No. This. By the way, I like that Baha is. Everyone, listen up. I like that Baha is feeling uneasy about this because how can you measure areas and you still use what? Can everyone? Can I ask you a question? What's the area of this classroom? Well, this classroom looks like a what roughly? A rectangle. So what do you need to measure? Just how many dimensions? 2. Length. Probably this is longer. And width. What do you measure the length in? For example, meters. Then what do you have to measure the width in? So what's meters times meters? So if I asked you right now, what's the area of a classroom or a field or something, you're gonna tell me what? Something in what? Meters squared or kilometers squared or miles squared. Well, guess what? Now we're using geometry, but with something that doesn't have fully what? Meters. Do you see what I mean here? You still can use a geometry concept to calculate something that has no what? No area in physical space. Do you see what I mean? All I care about is that the units have to what? Be treated the same as if the units of the what? Of the classroom. I'll tell you why. Because what's the height here? 8 what? What's the unit of this axis? See, now you have to be liberated from just geometry being what? Something on the ground. Geometry now is something that could be applied to anything that has how many dimensions? 2. And an axis has how many dimensions? An XY grid has how many dimensions? Guess what? We can apply geometry to it. It doesn't have the same meaning as an area here, but it has some important meaning in kinematics. Question for you. What do you get if you multiply 6 times 8 divided by 2? How the heck did I get meters? How could the area of this triangle be meters and not meters squared? I just told you the area is in meters squared. How come it's just meters inside? Thank you. Because what do you get if you multiplied meters per minute times minute? What happens to the minutes above and below? You see, when you multiply numbers, you also multiply the what with them? The units. And you deal with whatever the units tell you. What happens to the minutes? Goes with it. And what only survives? Meters. Can you tell me what you measure using meters? No. No. In kinematics, what do you measure using meters? Distance. Ladies and gentlemen, by adding up all the areas, I'm going to know how much distance the car went with a what? With a changing velocity. Do you see what I mean now? I'm not going to have the area of the distance. I'm going to have the value of the what? The value of the distance. That's why always know now that units still play a role even when you don't have geometry. All right, what's my next one? Okay, why meters? There you go. Because multiply units says so. There you go. See, now you know that math and physics always what? Support each other. Okay, so let's do the rest. What about the second one? 3 minutes times what? 8 minutes per minute. However, do you divide by 2 here? No, that's not a triangle. That's a rectangle. You just go legit, length time width. And what do you do with all the numbers inside of the shapes? You add them up. And if your car went according to that velocity profile, ladies and gentlemen, it would have gone through 276 meters of distance that way. I believe it was south. Guess what? That's legit what they do in first year calculus. But they do it with what? Not just with lines. They can do it with what? With curves because they learned calculus. Calculus was invented to solve a weird profile if it doesn't have lines. That's it.